So this is our first distance formula from a point to something else, a point in a plane in this case. So now let's take a, since we're talking about distances, let's do another distance, and let's talk about a couple of planes in space. We have to imagine the planes go infinitely outward, although a lot of times when we look at a plane, when I draw a plane, I usually just draw a rectangle, like a piece of paper. But the idea is that it goes on forever. So the question is, if you have two planes, what are the possibilities that can happen with those two planes? They're the same. They're parallel, aligned. So they could be perpendicular, but if they're perpendicular, they're essentially intersecting. And if we're talking about planes, the word skewed wouldn't apply to the planes. So those would be lines. We'll talk about lines later. So two possibilities for planes in space. One is that they're parallel, and we'll not consider the possibility that they're exactly the same plane. But when you're dealing with like three equations and three unknowns, I don't know if you did any of that kind of work in linear algebra or in that was actually covered in algebra, and I don't know if it's at the end of elementary algebra or the beginning of intermediate algebra. But they talk about like solving three equations and three unknowns. Systems of equations. Systems of linear equations. But when you're solving for three equations and three unknowns, you're essentially trying to figure out what's happening with three different planes going on. And there's a possibility that a couple of planes are the same. So in this case, we're just looking at two planes, and so your planes are either parallel or they intersect. Infinite planes. And when they intersect, when the planes intersect, what can you say about how they intersect, or where they intersect, or what do they intersect, or they would, if they intersect, they would intersect in a line. So if you have two pieces of paper and you hold them up in space and they're not exactly parallel, if you pretend that they extend to go on forever, they will eventually intersect. And when they do intersect, they will intersect in a line. So this is just a little snapshot of the intersection. But when they do intersect, it's a line. So let's consider both of these scenarios, and if they don't intersect, if they are parallel and they don't intersect, then that means there must be some distance between them. So I'd be interested in finding a distance between two parallel planes. So if the planes are parallel, it turns out that we can find the distance between them. Yeah. Yeah, that's exactly what we're going to do. So how are we going to find the distance between two planes? Well, Frederick just kind of blew it for us. But what he said was that if you just randomly pick any point on one plane and identify the other plane, then this is just a point and a plane, and we already know that formula. Okay? So let's talk about these planes. Let's say this plane is AX plus BY plus CZ is equal to D. What can you tell me about the other plane, if they're parallel? It has the same normal vector. But they would have a different D, right? So let's call one D1, let's call the other one D2. So if we're going to find the distance between these two planes, we're going to want to do that vertical distance business. But what we really need is just to randomly pick a point on one plane and just do the formula, right? So what if we randomly pick a point over here, and let's call it like we did that random point out in space. Just call it x1, y1, z1. And then we'll use a distance formula. So I'm using this plane and this point. So that's, according to the formula that I just wrote down on the previous page, this is AX1 plus BX2, BY2. Oops, 1, BY1. So we have the distance formula. Well, that looks the same as the other one. Can I simplify this any? Right. Yeah, you guys cool up to here? Right. I basically rewrote this thing over here, right? Yeah, this is D2 instead of minus D, because this is our D value for the plane. That's 1. Sorry, we don't have any Y2s. All right. Well, let's think about this. X1, Y1, Z1 is on the second plane, right? And this is essentially like taking the dot product of the normal vector and any point on the second plane. Isn't that just D1? So that's just D1. So not that you need to memorize this, but now you have an even nicer formula for the distance between two planes. Pretty cool, huh? Okay, any questions? Should we do an example? I don't even know if it's worth doing an example for this. So easy. So I need two parallel planes. 3x minus 2y plus what? 20z equals. So for this to be parallel, I need to have the same normal vector, right? And for this to be not the same line, I need a different number for the d. No, I already put 2. So then the distance, that's a 20. A little overzealous on my 0. So then the distance is, we're basically done with this problem. You know what I mean? And, you know, and that's it. We're done. I mean, I'm done.
Do the bars do anything for the negative 1 and minus 2?
Absolute value. So just to make it positive. Yeah. What is it? This is closer than I thought. Oh, are you sure? 1.08? Oh, yeah, it could be. Yeah. Okay, confirmed. Told you we're done. Yeah. It doesn't matter because it does. If you switch the order, then it'll just be the opposite. And since you're doing the absolute value, everything will turn to positive. So, do you hear the question? How do you initiate which one's D1, D2? And the fact that this is an absolute value, it's finding the difference, means it doesn't really matter which one comes first. Okay? So there's another distance question, is that distance between a point and a line. That one's a little more difficult, so I'll let you guys think about that. Let's do the intersection. By the way, we're good with this, right? Okay. So now the idea of intersection is a little bit trickier, especially for planes. We want to find out when two planes would intersect. And just by kind of logic or just by thinking about it, trying to visualize it, it seems like it would intersect in a line. And that kind of makes sense. So I think an interesting thing for us to be able to find is to be able to find out what that equation of that line is. Along the way, we'll see there's a lot of, not a lot, but a couple of other interesting things for us to consider to pick up. And so that's what we'll do. I know that these planes have a distinctive direction, and although we don't call it a direction, the normal kind of gives it a direction, right? If you just hold your pen or pencil up in space somewhere and pretend that's a normal to a plane, then you know exactly where that plane or how that plane is going to look like. So the normal vector has a lot of information about the plane. Yeah?
Are planes always infinite, or can they be bounded?
We'd like to just consider infinite planes.
Okay, so that's an infinite line.
Yeah. Yeah. But there might be some time where we might be interested in, yeah. So for now, let's take a look at the normal vector to each of these planes. Not necessarily. If the planes themselves are perpendicular, does that make sense? If the planes are perpendicular, then you would expect the normals to be perpendicular. But if the planes are not perpendicular to each other, then we don't expect that. Okay? What'd you say, Sienna?
I said you could use the normal vector in a dot product to find the cosine of the angle between the two planes. It doesn't give you the line, it gives you the angle between them.
Okay, that's a good start. Let's find that. So you got two vectors, right? Now, you guys all have notebooks and books. Tilt a page of your notebook a little bit and put a normal vector on each of those planes. Right? So tilt it a little bit. Now, look at the angle between those two pages that you have, right? Now, imagine, maybe you might need a friend to help you, to put a normal vector for each of those planes and look at the angle between those two normal vectors. All right. I can't draw a notebook.
So we're trying to find the angle between the two planes?
Yeah.
So can we just assume that the two vectors are going to intersect at the same point? Okay. Find the angle between that.
It would be the same. Exactly. So
we have to, it would be head to head, right?
well, that's the thing with vectors, right? The vectors can float around wherever you want. So I have these two vectors. Let me redraw my vectors.
So those normal vectors, you could increase the size of those lines on the drawing to the left.
Yeah,
And would they
could.
intersect?
Yeah, and that's how
Oh,
you
what happened?
And would the angle of at the intersection point between the normal vectors be the angle of the intersection point of the two points?
Yeah.
Product, you get the cosine.
So it turns out that the angle here between, the pages in your notebook is the same as the angle of those two normal vectors, because those vectors are perpendicular after all. They've just been like shifted or twisted by 90 degrees.
What's the property of geometric function?
Yeah.
Is it there or something?
Yeah. I don't know. Transitive? No. So anyways, we could start with that idea.
So did he just hold it, right? For that one, you just kind of hold it?
Yeah. Just fold the two planes.
The first one, if you increase the little purple line and they intersect, that also is better visual for other people. You know what I'm saying?
If what?
The first drawing, if the intersecting line, yeah, if you increase that blue line and that purple line, they eventually intersect.
Oh.
Yeah,
But then we
that
have
might be
to-
a nice way to show it to people too.
But then we have to increase the magnitude.
Well, this is for, you can just do like dotted lines too to show that they will.
Yeah. Well, I kind of drew it over
Yeah,
here.
you drew it anyway. Yeah, I'm just, that's a nice way to look at it. Yeah,
So it's the same as the angle between the normals. So the dot product will help us find this. So this doesn't help too much in finding the intersection that we're looking for, but this is a nice find. It's like you're looking for a treasure and you found something else that's useful. You found some shells. Nice gold shells. At least now you can do a couple homework problems, because I think this is a homework problem type of question. Now let's get back to the intersection of that line idea. So these two vectors will play a part in the intersection of a line. What do we need for a line in general? 2 points? We can use 2 points, but remember our key thing to come up with we need a point and a direction. So we need a point and a direction vector. Okay? Finding the point here will be a little tricky, but finding the direction is almost there. Are you guys doing that thing on your notebooks again? Do that thing with your notebook. I'll do it. So we've established that the angle between the two vectors, the two normal vectors, is the same as the angle between the two planes, right? So now I have these two vectors that I want to work with. I want to find, what do we need? We need a point and a direction.
Cross product.
You're just blowing it from me, yeah.
Sorry.
The cross product. You take these two vectors, right? When you cross them, you get a vector that's perpendicular to these two normal vectors. Now look at that vector that's perpendicular to these two normal vectors. Whether you cross it, doesn't matter which way you cross it, right? It goes in the same direction as that line. Okay? Yeah, that's later. Yeah. So you call it N1 and N2. Let's call it N1 and N2.
Oh, because it's perpendicular to those 2 points, so they're gonna fall on one point.
So it turns out that the cross product of N1 and N2, and depending on how you cross it, N1 cross N2, using the right-hand rule, gives you a direction. Whether it's going, to the left or to the right doesn't matter, as long as it's going in the same direction as the line. We're all good. So that's perpendicular to these two vectors, which is perpendicular to both planes, which means it must be on this line somewhere. I probably should have changed the color on that one. The cross product does put out a vector, and that vector will be perpendicular to the two vectors that you're crossing.
So assuming we didn't have any points and we're just going symbolically, how would we write the alpha? Would it be N1, N2?
Yeah, this one's a little trickier, because I don't think that you have N1 and N2, which is like A1, B1, C1.
Yeah.
This one, I don't think they come up with a nice formula like the last two that we just did. They don't have a nice formula for this, because it's kind of more of a process than using a formula.
But I was just asking, what I could write as a placeholder, so just
N1 and N2.
vector or something.
Well, you just call it N1 and N2, and then the cross product will be N1 cross N2, and just leave it like that.
Okay.
Or, yeah, because I was going to say you can call it D, but then that's another.
Yeah.
You can call it N1 and N2. Just so we have a direction. Oscar wants to find a point. Finding the point is a little trickier now, and finding the point is I don't want to say it's guessing, but it's guessing. And what we're going to do is we're going to assume this may or may not happen depending on what you get for N1 and N2, But we're going to assume that this will eventually hit one of your coordinate planes, either z is equal to 0 or x is equal to 0 or y is equal to 0. So finding a point, so we need a direction. Got it. So to find a point, we're going to let one of the variables equal to 0, assuming it's going to hit a coordinate plane. And what we're going to get out of this is we're going to put this back into the equation, into the equations. There's two of them, and then solve for x and y. So depending on what you let equal to 0, put into plane equations. Yes. And get x, or get y and z, assuming that we let x equal to 0. So we're going to put either x equal to 0 and get y and z from the equations of the planes, or we're going to let y equal to 0 and then we'll get x and z, or we'll let z equal to 0 and get x and y. But in any case, we'll get 0, comma, some number, comma, some number, and that point will be on the plane. It'll actually be on both planes. But more importantly, it'll be on that line. So let's do an example. So let's make a couple of planes. They have to be not parallel, so the normals have to be different. So let's give me an example of plane.
X plus 3y plus 5z equals 7.
Okay, somebody else give me a different plane that's not parallel.
Negative 3x plus 4y
Why?
All right, this is what we're going to do. What are we going to do again? Oh, we need to find a direction vector. So let's find a direction vector first. So the direction vector that we have would be 1, 3, 5. So that's the vector for the first. Vector for the second is -3, 4, 7. So if you were interested along the way to find the angle between these two planes, you would, dot the product and dot product it, dot the vectors and stuff. If you're interested in finding the angle, some cosine inverse or something. But we just want to go straight to the direction. So let's cross these.
I think it's 1, -22, 13. I'm going to hold on here until somebody says okay. Can you guys cross it? Did I hear a yes? By the way, so the quiz tomorrow will be on the cross product, so you guys got to know how to cross things.
Oh, that's cross product. Maybe I shouldn't put that there.
Yeah, that's right.
You got it right? All right, we got a couple of nods, and that's good enough for me. So we have a direction vector. So that was the easy part, right? I hope. Now, what we need to do is we need to find out a point. So what we're going to do is we're going to pick a variable and set it equal to 0. So what are we going to set equal to 0?
Z.
So let's let z equal to 0. Z equals 0. And then I'm going to come up with two equations and two unknowns. So when I let z equal to 0, I'm going to put it back into the planes. So I have x plus 3y plus 0 is equal to 7. Negative 3x plus 4y plus 0 is equal to 100. All right, well, you guys figure it out. I'm going to use Wolfram Alpha. Yeah. I think they can read it. I seem to have something.
Yeah, this is really ugly. Yeah. Y equals 121 over 13, and x equals horrible. 2,393 over 13. That might be wrong.
You got the x. That was good. Or the y. You got the y. The x is, looks like it's negative.
Yeah, x is, yeah, no, that's definitely what I said was definitely wrong.
All right.
The first the x is right.
All right, so good. We have a point. Our point is x is equal to negative 272 over 13, 121 over 13 for the y. Oh, what's our 0? I mean, what's our 0? What's our z? 0. So we have a point and we have a direction. So we're done. Well, kind of. So this point, as ugly as it is, what's significant about this point? It's what? It's on the line. It's on the intersection between the two planes. It's also on the xy plane, right? Because z is equal to 0 is the xy plane, and that's, we were banking on this line to actually eventually hit the xy plane. You want to see a graph of this? So this is your equation of the line.
Yeah. No, I'm not
Yeah.
How distributing would you take this as in the R naught plus BT form?
Yeah, that's what I have.
Yeah,
I,
because sometimes the homework wants you to do the distribution to get it into the actual equation.
yeah.
Would you take that?
Yeah.
I feel like I'm gonna have a stroke in this class sometimes. I'm just like
A stroke. Sorry, I'm going to move things around a little bit just so I can start getting the visual. So let's start off with the planes.
I don't know why I clarified that, but I clarified it.
So that 100 really puts a damper on things.
Yeah, thanks for that one.
Getting closer. So eventually, if like that one plane is really far away, eventually they will intersect if we just keep going. So this is what we were seeing, before. They look like they're pretty far away from each other, but the zooming in business or zooming out, eventually they will intersect, and if you look at the intersection, they actually intersect in the line. Okay? So now let's see if we can throw that line in. Now that line is a little tricky because it's got a lot of fractions, but this is a computer, so can you help me get that? What's that? Negative? What? 272 over 13?
Negative.
Uh-huh. Next one? And then 0. Oh, maybe we should have put this down first. That's the point that we found. All right, so let's actually find that line.
And then let's say that putting z equals 0 is going to be the intersection point. You just got to keep, then you do the whole process again with x equals 0.
Yeah.
That doesn't work, y equals 0.
Yeah.
And if all those fail, I guess that means they obviously don't intersect and call it a day.
No, that means you did some algebra wrong. I'm sorry, what is it? What's the D? And 13. Can't see it. Let's make it thicker. Let's make it thicker. Well, that's a little thick. Wow. 3. Two. Now remember, this is a parametric equation that's only going to be drawn as far as the vector. So if we change the t limits, these are t values, to go basically minus infinity to infinity. So -3, that's not quite infinity, but -5 to 5. I'll cover it. And so this line is actually going through those two planes, and that's the intersection that we found. That looks too thick. All right, let's see if we can get a nice picture of this in our notes. Right there? No.
I figured out.
All right. You guys even look at the notes?
Yeah. I have.
Okay. All right, so now we got the intersection of two planes. Let's do another intersection. Let's do an intersection of a plane and a line. So if you have a plane and a line in space, what are the possibilities that can happen? The line can be on the plane. They can intersect at one point, or they're parallel to each other somehow.
With lines or with planes, by definition, they can't just intersect on one line, right? They have to intersect on a line.
Oh, if you have two planes? Yeah, if you have two planes, then they have to intersect in a line.
Two lines and they intersect at the exact.
Yeah. We'll talk about the intersection of two lines later, if there is a later. Yeah, you can have it not intersect in 4D. All right. So two possibilities, or I don't know how many possibilities we came up with, but one possibility is that that line can actually be on the plane. The line could be parallel to the plane and not intersect, or the line can actually intersect the plane.
The line, the intersection between two planes, but in more dimensions.
That's what that's what he was talking about. Then you'll just have an extra variable to mess around with.
Some weird numbers if you go to like 3D state or 4D
Yeah,
state,
so
intersecting on a 3D state.
I don't know. I haven't thought about that much. Then it would, right. So it would intersect in a space. Ooh. It could possibly intersect in a space. Yeah. Let's talk about that another time. All right. So let's briefly talk about when the line is on the plane. How would you know if the line is on the plane? Well, the normal is the normal to the plane, but the line doesn't have a, quote, normal. They're what? No. Well, the plane doesn't have a direction. Well, what's the direction for the plane? You got it. So the direction for the plane is a normal. So would that make it on the plane? So if you dot the normal vector from the plane, and then you dot it with the direction vector, and you get 0, does that mean that this is on the plane? No. Why not? It's perpendicular to the plane. So that's kind of like the same scenario here, right? If this is going in the same direction as a plane, and you dot these two vectors, then they would also be equal to 0. So dotting those two vectors doesn't guarantee that the line is actually on the plane. It guarantees that it's parallel to the plane.
So it needs both for the dot product to be 0 and 8 points of the line to be 8 points on the plane.
And you need that point on the line to be a point on the plane. So let's consider a point on the line. It doesn't matter where. Let's consider a point on the line. What should we call it? X1?
So I assume all of this is required to always have a point in the direction.
Yeah. Do you guys understand that? When you see an equation of a line, you should be able to pull out the point and the direction of that line. So the line can either look like a parametric equation. So this x is equal to something plus something t, right? So the other form is the vector equation, in which case you have a point plus t times the direction. That's even easier. And then the third form is the symmetric form, which you should be able to extract information out.
Is the symmetric form like x over 8 is equal to y?
Yeah.
Okay.
So what you could do is once you find a point on a plane or find point on the line, and then you can dot it with the normal. What should you get when you dot the point on the line with the normal?
0.
No? It's a scalar, but what's that scalar?
The point on the line.
Not 1. Here, what if I write the equation of the plane? You're thinking it, Joe. It's not called the distance. It's just d. You should get the d from the plane,
Oh, of course.
right? Because this point is on the plane, and whenever you dot the normal with any point on the plane, you should get d. So if this happens, you don't even have to dot the normal in the direction. You just consider the point. So if this happens, then the point is, the line is on the plane. Okay?
So going on that, if we dot the point and the normal, and we don't get d, it's parallel but not on.
Right. Well, and also the n dot this d is equal to 0.
Yeah.
So if line is not on the plane and the normal vector dotted with the direction vector is equal to 0, then the line is parallel to the plane. That's your second option choice. So you kind of have to go through this in sequence and progression. And if that's not the case, then the line and plane must intersect. So if n dot d is not equal to 0, then that means the direction vector is not perpendicular to the line. So eventually, they will intersect. Okay? So the question is, how do you find an intersection? So here's what you're going to do. Write the line in parametric form. So that would be x of t, y of t, z of t. So you can see the x, y, and z individually as a function of t, And there are linear functions of t, so it's just going to be a plus t, b, or whatever. Once you get those x equals, y equals, z equals, plug it into the plane. So when you plug the x equals something into the plane, then your plane would just have t's in it. And then when your plane only has t's in it, you should be able to solve for that. Yeah, so you plug that t back in. Solve for t. And then after you find t, plug t into the line equation. To get your point x, y, z. Okay? I'm not going to do an example of this because I have 5 minutes to talk about two lines. So let's talk about 2 lines real quick. So when you have a couple of pencils and you throw them up in space and then they freeze in space, what are the possibilities that could happen? They could be they can intersect, and if they intersect, they would intersect at one point. They could be parallel to each other. But it turns out that in space, if they're not parallel to each other and they don't intersect, there's another option, and that's called skew. So skew is when they're not parallel, but they also don't intersect. That's same with a plane. Yeah, that can happen in a plane in 3 dimensions or 4 dimensions. All right? So how would you find out if the 2 planes are parallel? Do they have to be exactly the same?
No, scaled up version of each other.
Okay.
You can multiply or divide by to get the other one.
So if the 2 directions, are scalar multiples of each other, then they are parallel. So in sequence of what you want to do if you're faced with a problem with 2 lines, this is the first step that you take. You try to find out if they're parallel. If they're not parallel, you see if they intersect. This is your second step. You see if they intersect. And if they're not parallel and they don't intersect, then they're skewed. If not parallel and don't intersect, then they are skewed. Skew. Okay? So I'm leaving this part out because this part is a little bit more involved. The tricky part about this is that the lines can pass through the same point, but they can pass through the same point at different times, right? So your line for the first equation would have some t value in it, and then your line for the second one would also have some t value in it. So if they do intersect, they might intersect at different t values. So what you need to do is you need to call the one line with a t and then the other line with a different parameter t. So you might need to use s. So this is problem number 3 in the worksheet. And what I want you to do is I want you to try to do it at home. And just problem number 3. I don't care about the rest. Actually, you might as well do problem number 4 too. So I'm interested in seeing problems number 3 and 4. Each of them will be worth half of a point on the exam if you bring the solutions tomorrow. Okay? From the worksheet that was done yesterday. So what I'm going to do is I'm going to write up the solutions for that, and I will show you after tomorrow. I'll post it online. But I want you to try it, look through some resources, and see if you could do it. Okay?
I actually did it yesterday.